Good morning. Today I Anshu from BSc Chemistry on our first year. Today I want to read chapter Electrochemistry. Electrochemistry of Physical Chemistry. Section A, Electrical Transport, Electrolytic and Metallic Conduction. Substances which allow electricity to pass through them are known as conductor, whereas substances which do not allow electricity to pass through are known as insulator. Conductors are divided into two classes: those which conduct electricity without undergoing any decomposition. These are called electronic conductors. Example: metal, graphite, and certain minerals. As the name indicated, the conduction in this case is due to the flow of electron. Those which undergo decomposition when current is passed through their aqueous solution or melt, these are known as electrolytic conductors or electrolytic. Example: solution of acid and base, salt and water, fused salt, etc. In this case, the flow of electricity is due to movement of ions. Electrolytes are further classified into two main categories as strong electrolyte and weak electrolyte. Strong electrolytes are the substances like strong acid, example HCl, HNO3, H2SO4, etc. Strong bases, example NaOH and KOH, etc. Most of the inorganic salts these dissociated almost completely in the aqueous solution or in the molten state and hence conduct electricity to a large extent. Weak electrolytes are substances like weak acid, example CH3COH, HCN, CH2, H2CO3, H3PO4, etc. Weak bases, example NH4OH, calcium hydroxide, aluminium hydroxide, etc. These have low degree of dissociation and hence conduct electricity to a small extent. Substances like sugar, urea, etc. The solution which do not conduct electricity are known as non-electrolytes. Factor affecting electrolytic conduction. The conductions of the solution of an electrolyte depends upon the following factors: interionic attraction, which depends upon the interaction between the ions of the solute and hence called solute-solute interaction. On the basis of the substance are classified as the strong electrolyte and weak electrolyte, as already mentioned. Solvation of ion, which depends upon the interaction between the ions of the solute and the molecules of the solvent and hence are called solute-solvent interaction. Viscosity of the solvent depends upon the solvent-solvent interaction. The effect of all these factors decrease with increase of temperature, hence the electrolytic conduction increase with increase of temperature. On the other hand, the electrical conduction of electronic conductors decrease with increase of temperature. Alternatively, the factor on which the electrolytic conduction depends are as follows. Nature of electrolyte: strong electrolyte ionize almost completely in the solution and have conduct electricity to a large extent, whereas weak electrolyte ionize to a small extent and hence could conduct electricity also to a small extent. Nature of solvent: electrolytes ionize more in polar solvent, hence greater the polarity of the solvent, greater is the ionization and hence greater is the conduction. Concentration of solution: higher the concentration of the solution, less is the conduction. This is because in weak electrolyte the ionization is less, where in strong electrolyte the interionic attraction are higher at higher concentration. With dilution, interionic attraction decreases and hence conduction increases. Temperature: on increase the temperature, the dissociation increases and hence conduction increases. Difference between metallic conductor and electrolytic conductor. The main point of the difference between metallic conductor and electrolytic conductor are mentioned, summed up in table 6.61. Difference between metallic conductor and electrolytic conductor. Metallic conductor: flow of electricity take place without the decomposition of substance. Flow of electricity is due to the flow of electron only, that is, there is no flow of matter. The conductance depends upon the structure and density of metal and the number of valence electron per atom. The electrical conduction decreases with increase of temperature. This is because kernel starts vibrating, which produce hindrance in the flow of electron. The resistance offered by metal is also due to vibrating kernels. Electrolytic conductors: flow of electricity take place accompanied by the decomposition of substance. Electrolyte: flow of electricity is due to movement of ions and hence there is flow of matter. The electrical conduction increase with increase of temperature. This is generally due to increase in dissociation or degree in the interionic attraction. The resistance shown by electrolytic solution is due to factors like interionic attraction, viscosity of solvent, etc. Electrical resistance and conduction. Every substance offers resistance to flow. The flow of electricity to small or large extent. This law that gives the exact value of resistance is known as Ohm's law. It states that if to the ends of the conductor voltage E is applied and a current I flow through it, then the resistance R of the conductor is E by I. Current is generally measured in ampere, whereas voltage is measured in volts. If 1 ampere current flow through a conductor when a voltage of 1 volt is applied to it, resistance of conductor is taken in 1 ohm. Thus, according to Ohm's law, R is equals to E by I, or ohms is equals to volts by ampere. In terms of SI base unit, this is explained below. It is seen that like metallic conductor, solution of all electrolytes also obey Ohm's law. It is obvious that a substance which offers greater resistance will allow less electricity to flow. This results also follow from Ohm's law. This also follows from Ohm's law, according to which I is directly proportional to 1 by R. The reciprocal of electrical resistance is called the conductance. It is usually represented by C. Thus, C is equals to 1 by R. It is common practice to speak of the conduction of solution rather than its resistance unit. The unit of conductance are Siemens or reciprocal ohm, written as ohm inverse or mho or rho. For example, if a solution has a resistance of 10 ohm, it is said to have a conductance of 1 by 10 ohm inverse, or 1 by 10 mhos, or 1 by 10, or 1 by 10 Siemens. Specific equivalent or molar conductivity. Specific conductivity, or simply conductivity, it is observed that resistance R of a conductor is directly proportional to its length of a conductor and inversely proportional to its area of cross section, where rho is a constant of proportionality called specific resistance or resistivity. Its value depends upon the material of a conductor. The reciprocal or resistivity is known as specific conductivity, or simply conductivity. It is denoted by kappa, and thus if the specific conductivity and C is the conductance of the solution, then R is equals to 1 by C. Now, if L is equals to 1 centimeter and A is equals to 1 square centimeter, then K is equals to C. Hence, specific conductivity of a solution is defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. Alternatively, it may be defined as the conductance of 1 centimeter cube of the solution electrolyte, or in terms of SI base unit, it is defined as the conductance of 1 meter cube of the conductor. If the volume of the solution is V centimeter cube, the specific conductivity of such a solution at this dilution V is written as kV. Similarly, at concentration C, it is represented as Kc. Unit resistivity rho is equals to R is equals to A by L, ohm centimeter square by centimeter, ohm centimeter, or ohm centimeter. Specific conductivity is equals to 1 by rho, 1 by ohm centimeter, that is equals to 1 Siemens centimeter inverse. Equivalent conductivity. For example, for comparing the conductance of the solution of different electrolyte, it is essential that the volume of solution should be same and they must contain such definite amount of electrolyte which gives ions carrying the same total charge. The best choice is therefore to consider the solution having equal volume and containing their corresponding gram equivalent weight. The conductance of such a solution is called its equivalent conductivity. Hence, equivalent conductivity of a solution at dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of an electrolyte dissolved in V centimeter cube of a solution. When the distance between the electrode is 1 centimeter and the area of electrode is so large that whole the solution contained between them, it is represented by lambda. Relationship between equivalent conductivity and specific conductivity. Equivalent conductivity of a solution is usually not found directly but is calculated from the specific conductivity. The relationship between equivalent conductivity and specific conductivity may be obtained as follows. Consider a rectangular vessel with its two opposite walls, one can 1 centimeter apart and made of some metal sheets so that these act as a electrode. Case 1. Suppose 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken in a vessel. The conductance of this solution will be then its specific conductivity. Further, if 1 centimeter cube of the solution taken contains 1 gram equivalent of electrolyte, the conductance of the solution will be its equivalent conductivity. Thus, when 1 centimeter cube of the solution containing 1 gram equivalent of electrolyte is considered, the equivalent conductivity is equals to its specific conductivity. Case 2. Suppose 4 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken in the conductance of the solution will be still equal to its equivalent conductivity at this dilution, but now there will be 4 cubes each of volume 1 centimeter cube as shown in figure. The conductance of each 1 centimeter cube of the solution is equals to its specific conductivity, so that the total conductance of the solution, that is equivalent conductivity, is 4 times the specific conductivity. In general, if the volume of the solution containing 1 gram equivalent of electrolyte is V centimeter cube, we have equivalent conductivity equals to specific conductivity into V. In terms of concentration, if the solution has concentration of C gram equivalent per liter, that is C gram equivalent are present in 1 centimeter cubes and of the solution, then the volume of the solution containing 1 gram equivalent will be 1000 by C. Hence, the above expression may be written as lambda equivalent is equals to Kc into 1000 by C equivalent. Kc into 1000 by normality. Note carefully that in the above expression V is the volume of the solution in centimeter cube and containing 1 gram equivalent of electrolyte, and C is the concentration in gram equivalent per liter. Molar conductivity of a solution is defined as in a manner similarly to that of the equivalent conductivity as under. Molar conductivity of a solution at a dilution V is the conductance of all the ions produced from the 1 mole of electrolyte dissolved in V centimeter cube of the solution when the electrodes are 1 centimeter apart and the area of electrode is so large that the whole of the solution is contained between them. It is usually represented by lambda m. Relation between molar conductivity and specific conductivity. As in the case of equivalent conductivity, the molar conductivity is related to the specific conductivity as follows. Variation of conductance, specific conductivity, equivalent and conductivity, and molar conductivity with dilution. In general, electrolytic conduction as well as equivalent conductivity and molar conductivity increase with dilution, whereas the specific conductivity of an electrolytic solution decrease with dilution. The reason for which such a behavior are briefly explained below. The conductance of the solution is due to the presence of ions in the solution. The greater the number of ions, greater is the conductance. As on dilution, more ions are produced in solution, so the conductance should also increase on dilution. The specific conductivity of an electrolyte falls with dilution because the number of current carrying particles, that is ions, present per centimeter cube of the solution become less and less on dilution. However, the increase of equivalent and molar conductivity on dilution is due to the fact that these are the product of specific conductivity and the volume V of the solution containing 1 gram equivalent or 1 mole of electrolyte. As the decreased value of specific conductivity is more than compensated by the increasing value of V, so the value of lambda equivalent and lambda m increase with dilution. Variation of molar conductivity with concentration. As already mentioned in the beginning of this section, there are two types of electrolytes, namely strong electrolyte and weak electrolyte. The variation of molar conductance with concentration for each of these electrolytes is briefly discussed below. Conductance behavior of strong electrolyte. As discussed later in more details in section 6.13, the molar conductivity of strong electrolyte is found to be vary with concentration according to equation, where B is the constant depending upon the type of the electrolyte, the nature of the solvent, and the temperature, and delta m naught is the molar conductivity at infinite dilution, called limiting molar conductivity. This equation is called Debye-Huckel-Onsager equation, is found to hold good at low concentration. Thus, if delta m is plotted against delta c, a linear graph is obtained for low concentration, but it is not linear for the higher concentration, as shown in figure 6.5, in which KCl has been taken as an example of strong electrolyte. Further, the curve obtained for a strong electrolyte shown there is a small increase in conductance with dilution. This is because a strong electrolyte is completely dissociated in solution, and so the number of ions remain constant at higher concentration. The greater intrionic attraction retards the motion of ions, and therefore the conductance falls with increased concentration. With decrease in concentration, that is with the dilution, the ions are far apart, and therefore the intrionic attraction decreases, due to which the conductance increase with dilution and approach a maximum limiting value at infinite dilution, designs as delta m naught or lambda infinity m. Conductance behavior of weak electrolyte. A weak electrolyte dissociates to much lesser extent as compared to stronger electrolyte. Therefore, the conductance of weak electrolyte is much lower than that of strong electrolyte. At the same concentration, this is shown in figure 6.5, in which an acetic acid has been taken of strong electrolyte. At the same concentration, this is shown in figure 6.5, in which acetic acid has been taken for example of weak electrolyte. Further, the curve obtained for a weak electrolyte shows that there is a very large increase in conductance with dilution, especially nearly infinite dilution. This is because as the concentration of weak electrolyte is reduced, more of its ionized. Thus, increase in conductance with decrease in concentration is due to increase the number of ions of the solution. However, it is not reaching a limiting value. Theory of ionization and Oswald dilution law. Arrhenius theory of ionization or electrolytic dissociation to explain a number of phenomena related to electrolyte, such as conductance, electrolysis, anomalous behavior of electrolyte towards colligative property, a higher value of osmotic pressure, elevation in boiling point, depression in freezing point, lowering of vapor pressure than expected. Arrhenius in 1887 put forward a theory about electrolytes. This theory is called Arrhenius theory of electrolyte dissociation. The main point of this theory is modified form of summarized below. Limitation of Arrhenius theory. No doubt Arrhenius theory was able to explain a number of facts and phenomena, but soon a number of objections were raised against this theory, especially when applied to strong electrolyte. A few of these objections are as follows. Arrhenius suggests that ionization of an electrolyte takes place when dissolved in water. However, X-ray studies have shown that many such electrolytes are already ionized state. Hence, the word ionization has been replaced by the word dissociation. An electrolyte can be conduct electricity even in molten state. It shows that dissociation of the electrolyte takes place even in molten state. As such, the function of water could be explained by Arrhenius theory. In other words, it could not explain by dissociation take place at all. The most serious objection against the Arrhenius theory was its utter failure when applied to strong electrolyte. Example, Ostwald dilution law, which is derived on the basis of Arrhenius theory using the concept of ionic equilibrium, fails for the strong electrolyte. That is, constant value of dissociation constant K is not obtained. The degree of dissociation of strong electrolyte calculated from conductance measurement was found to be different from calculated from colligative property. The value were found nearly same only for univalent electrolytes. Strong electrolytes are almost completely dissociated even at moderate concentration, that is alpha equals to 1 or 100% at all concentration. Hence, Arrhenius view that conductance increase with dilution because the dissociation increase does not make any sense. In case of strong electrolyte, the increase in conductance with dilution must be therefore due to some other factors called intrionic effect discussed in the next section. The ratio delta C by delta M is therefore better called apparent degree of dissociation or conductance ratio only. The failure of Ostwald dilution law for strong electrolyte is evidently because of two reasons. Firstly, strong electrolyte are almost completely dissociated in the solution, therefore the question of equilibrium does not arise. Secondly, the calculation of delta from lambda C by lambda naught is faulty as mentioned above. Explanation of anomalous behavior of strong electrolyte. Intrionic effect. Debye-Heckel theory. The increase of equivalent conductance with the dilution in case of weak electrolytes can be easily explained on the basis of Arrhenius theory, which suggests that the conductance increase because the dissociation of the weak electrolyte increases with dilution. However, in case of strong electrolyte, as they are almost completely dissociated even at moderate concentration, the increase in equivalent conductance with dilution must be due to some other factor. The qualitative explanation put forward is as follows: the conductance of the solution of an electrolyte depends on not only upon the number of ions but also upon their speed. In the case of weak electrolyte, the increase in conductance with dilution is due to increase in dissociation of electrolyte. Due to increase in number of ions, the speed of the ions in this case are not much affected by change in concentration because the number of ions produced is so small. These causes are not much affected by change in concentration because the number of ions produced is so small that the distance between them is quite large, so that there is no interference in the movement of ion by the other ions. However, in the case of strong electrolyte, number of ions produced on dissociation is larger than the freedom of movement of anions in hindrance by the other ions present around. When the solution is diluted, the ionic interference decreases and hence ionic speed increases. So does the equivalent conductance. The first special successful attempt to explain the variation of equivalent conductance of strong electrolyte dilution was made by Debbie Huckel. The fundamental underlying their work is that because of electrical attraction among the opposite charges ion, each ion is surrounded by a large number of opposite charge ion, which may be regarded as ionic atmosphere opposite charges, and this affects the speed of the ions in an electric field. The electrical attraction among the opposite charge ion which affect the speed of an ion, the electrical field, are called interionic effect. There are two such effects which are briefly discussed below: relaxation effect or asymmetric effect. In this solution, each ion is surrounded by an ionic atmosphere of opposite charge, so the long as no electric field is applied, the ionic atmosphere remains symmetrical around the central line. However, when a current is passed through the solution, the central line moves towards the opposite charge electrode. As it moves out of the ionic atmosphere, it has to rebind an ionic atmosphere of opposite charge around it, and old ionic atmosphere dies out. However, neither the destruction of the old ionic atmosphere nor the formation of new ionic atmosphere take place instantaneously. Each of them take place sometime called time of relaxation. During this time, old ionic atmosphere pulls the moving ion backward and hence retards its motion. Hence, this effect is called relaxation effect. Alternatively, it may be argued that as the central lines move, the symmetry of the ionic atmosphere is lost. More ions of ionic atmosphere are left behind than are present on front. The excess ion of the ionic atmosphere present behind the moving ion drag ion backward and retard its motion. Thus, the effect arises because of the asymmetry of the ion atmosphere of the moving ions, and hence also called asymmetry effect. Electrophoretic effect: when EMF is applied, the central ions move in one direction and the opposite charge ions atmosphere move in opposite direction. As the ionic atmosphere moves, solvent molecules associated with it also move along with it. Thus, the flow of ionic atmosphere and that of solvent molecules attached to it take place in the direction opposite to that of movement of the central line. In the other words, the central line is moving against the stream, hence its motion is retarded. This effect is called electrophoretic effect, since it is not similar to that of opposing the movement of colloidal particles in an electric field. Beside the above two effects, the third retarding force is the normal frictional resistance offered by the medium, which is two tests can be readily performed to verify the Onsager equation. Fall in concentration in anodic compartment due to migration of Ag plus ions X minus Y gram equivalent. Further, from figure 6.12 it may be seen transport number as seen in section 6.14. When an electric current is passed, the ion migrates toward electrode, thus the electric current is carried by ions. Each ion carries a definite fraction of the total current depending upon its speed. The fraction of total current carried by ion is equals to transport number or transference number or Hitow's number. Greater the speed of ion, greater the amount of current it will carry, and hence greater will be its transport number. Let UA and UC be the speed of the anion and cation respectively. Current carried by the anion, current carried by the cation is inversely proportional to UC, which is equals to kinetic energy of UC. Since current is carried only by ions, total current carried is equals to current carried by anion plus current carried by cation. Transport number of an anion Na is equals to KUA by KUA plus UC. Similarly, transport number of cation will be Nc is equals to UC by UA plus UC. Factor on which transport number depends. It has been stated earlier that the transport number of an ion directly proportional to the nature of ion. Normally, the smaller the size of the ion, greater its speed, and hence higher is its transport number. For example, the transport number of H positive ion is 0.1 and HCl is greater than that of Na positive ion in the 0.1 and NaCl, or K positive ions in 0.1 and KCl, etc. Nature of other ions present. For example, the transport number of chlorine ion in HCl is different from that of chlorine ion in NaCl. This may be explained as follows, where UH positive, Na positive and UCl negative represent the speeds of H positive ion, Na positive and Cl negative ion respectively in their respective solution. As Na positive ion is larger in size than H positive ion, UH positive is greater than Na positive. As a result, the denominator of the expression 1 is greater than that of expression 2, and hence NCl negative is HCl is smaller than NCl negative in NaCl. Hydration of ion. The speed of the ion, hence its transport number, is very much affected by the hydration of ion. For example, Li positive ions are smaller in size than Na positive ions and hence may be expected to have higher transport number than Na positive ion, but the actual position is otherwise. This is because the lithium positive ions are more hydrated than Na positive ions. Similarly, Na positive ions have smaller transport number than K positive ion. Concentration. The transport number of an ion change with concentration, but the change in very small. However, in case of the increase in concentration results into the formation of a complex ion, the transport number changes significantly. For example, the transport number of cadmium plus 2 ions in cadmium dioxide solution falls from 0.44 to 0.00 m5 m solution to 0.003 m in a 0.025 m solution. At still higher concentration, the transport number appears to be 0 or even negative. This is explained on the basis of formation of the complex cadmium I2 negative ion at a higher concentration as follows in dilute solution. Temperature. As the temperature increases, the ion tends to approach transport number value 0.5, that is, at this temperature equal fraction of the current is carried by the cation and anion. In the case of anion having transport number less than 0.5 at ordinary case of the ion having transport number less than 0.5 at ordinary temperature, the transport number increases with increase of temperature. In case of ion having transport number greater than 0.5 at ordinary temperature, the transport number decreases with increase. At ordinary temperature, the transport number decreases with increase of temperature. When the transport number of ions are approximately 0.5, as in KCl, the effect of temperature is very small. Thank you.